I had this moment the other day that it really stopped me in my tracks. I was trying to remember the name of that psychological phenomenon where you see patterns in random things. Like a face in burnt toast.
Oh, right. Pareidolia.
Exactly. But here's the thing. I didn't know that word. I had absolutely no clue. So I pull out my phone and I type just this completely vague sentence. Seeing faces in inanimate objects.
Yeah.
And in maybe 0.2 seconds? Boom. First result. Pareidolia.
It feels like telepathy, doesn't it?
It really does. It feels like some kind of magic. The search engine just knew what I meant, even when I didn't have the words for it. But you and I both know it's not magic, it's engineering.
Oh, it is some of the most rigorous, most complex engineering in, well, human history.
Yeah.
And that's really the mission for our deep dive today. We're going to ruin the magic trick.
We're spoiling the illusion.
We are dismantling the black box. We're going to look at the actual science behind that split-second miracle, which is formerly known as information retrieval, or just IR.
And to guide us, we're not just, skimming a blog post. We are digging into a real heavy hitter of a text. This is Chapter 37 from Principles and Architectures of Modern Information Retrieval Systems by Xiaozu Mei and Dragomir Radev.
Yeah, this is a foundational text. It strips away the user interface, the pretty logo and the search bar, and it looks purely at the mathematics of how a machine, which understands zero nuance, can somehow understand human intent.
And that's the core definition the text gives, right? It's not just finding words, it's satisfying an information need.
That phrase is so crucial. Information need. You have this gap in your knowledge, a missing puzzle piece. And the system's job is to figure out the shape of that missing piece based on a really bad sketch you drew, which is your query, and then find the perfect match in a pile of billions of pieces.
So let's start with the problem itself, because I think we take for granted just how hard this is for a computer. The text uses a great, really specific example to illustrate this, the jaguar problem.
Yes, this is sort of the classic example of ambiguity. The author set up this tiny hypothetical database with just 3 documents. Document 1 says, Tom bought a car. Document 2 says, Jaguar is a big cat. And document 3 says, Tom saw a jaguar.
Okay, simple enough.
Then you, the user, come along and you talk the query, jaguar animal.
Right. So to me, a human with a brain, this is obvious. Document 2, Jaguar is a big cat. That's the best match. Document 3, Tom saw jaguars is a maybe. Tom could be at the zoo or he could be looking at a car. We don't know. And document 1, Tom bought a car, is just irrelevant.
Precisely. But now, try to look at it from the computer's perspective. It doesn't know what a cat is. It doesn't know who Tom is. And it certainly doesn't know that jaguar is a word with polysemy, multiple meanings. It just sees strings of code.
So the system somehow has to rank jaguar as a big cat at the very top, even though the word animal doesn't actually appear in that sentence.
Exactly. And it has to do this while dealing with the fact that your query is sparse, usually just 2 or 3 words, and it's noisy. It's a massive guessing game based on probability.
So how does it even start? How does a computer read these documents to even begin that guessing game?
Well, the first thing to get is that the computer isn't reading like you or I do. It's not looking for narrative or sentence structure. It uses a method the text describes as the vector space model, or more commonly, the bag of words.
Bag of words. I love that image. It sounds so destructive.
It is destructive. Imagine you take a beautiful article, right? You take a pair of scissors, you cut out every single individual word, you throw them all into a bag, and you just shake it up.
So the man bit the dog, and the dog bit the man.
Think of the exact same bag of words. Completely. The system doesn't care about order. It doesn't care about grammar. It just wants to know, is the word dog in the bag? Is bit in the bag?
That seems overly simple. Doesn't it lose a ton of meaning?
It does, but it's fast. And before it even starts counting the words, it cleans up the mess. It removes what are called stop words.
These are the filler words, like the and a.
The, is, and a, exactly. These words appear in almost every document in existence. They're just noise. If you search for the jaguar, the word the is useless for narrowing down the results, so the system just tosses it.
So it's decluttering the bag.
Right. And then it does stemming. It'll take words like fishing, fished, and fisher.
And chop them all down to their root. Fish?
Exactly. So it treats them all as the same concept. It standardizes the language. But here is where it gets really interesting and where the math kicks in. We have this bag of stemmed words. How do we turn that into something a computer can actually calculate?
The text talks about vectors. And I'll be honest, my high school geometry is a little rusty.
Well, think of it this way. Imagine a map. A standard map has 2 dimensions, right? Latitude and longitude, north, south, east, west. You could describe any location on Earth with just two numbers.
Okay, I'm with you. 2 numbers, 1 point.
Now, imagine a map where every single unique word in the English language is its own dimension. There's an axis for aardvark, an axis for apple, all the way to zebra.
Wait, there are, what, hundreds of thousands of words in English?
Correct. So we are talking about a map with maybe 100,000 dimensions.
My brain just broke trying to visualize that.
You can't visualize it, no. But mathematically, it's just a list of numbers. Every single document on the internet is just one point on this gigantic multi-dimensional map.
So if a web page has the word jaguar, it moves, say, 5 steps along the jaguar axis. But if it doesn't have the word pizza, it stays at 0 on the pizza axis.
Exactly. And because most documents only use a tiny fraction of all possible words, this map is mostly empty space. It's what's called a sparse vector. Just a long string of zeros with a few ones and twos scattered in there.
Okay, so we've turned the entire internet into this cloud of points floating in some crazy 100,000 dimensional space. But if I type in a search, does the computer have to scan every single one of those billions of points? I mean, that would take forever.
It would take weeks. You type Jaguar and get an answer next month. To make it instant, engineers use a very specific data structure called the inverted index.
And the source material compares this to the index at the back of a textbook, right?
It's the perfect analogy. When you want to find photosynthesis in a biology book, you don't start at page 1 and read every single word. You go to the back, you look for P, you find photosynthesis, and it just lists the page numbers, 42, 88, 112.
So the search engine basically has this master list of every word in existence. And next to the word jaguar, it just has a list of all the document IDs where it appears.
Document 2, document 3, document 400. Exactly. So when you hit search, the system goes straight to that one entry in the index, grabs those specific documents, and completely ignores the other trillion pages on the web. That's how it's so fast.
Okay, so we found the documents that contain the word. But just because document has jaguar in it doesn't mean it's the best one. What if I just wrote the word jaguar 5,000 times on a blank page?
Ugh. Keyword stuffing.
Mm.
The golden ticket of 1996. But the search engine's got a lot smarter. We need to measure importance, not just presence. And this leads us to arguably the most important concept in the entire text. TF-IDF.
TF-IDF. It sounds like a radio station call sign.
It does. It stands for Term Frequency Inverse Document Frequency. It's a weighting system. It assigns a score to every word in every document.
Let's break that down. Term frequency, TF. That seems straightforward.
It is. It's just wise.
Hmm.
How many times did the word appear in this specific document? If Jaguar shows up 20 times in document A and only once in document B, then document A is probably more about Jaguars. Higher TF score.
But that brings us back to my spammer problem. I can just repeat the word over and over to get a high TF score.
And that is why we need the second half, IDS, Inverse Document Frequency. This measures how rare the word is across the entire internet.
Okay, give me an example of how that works.
So let's go back to your query, Jaguar animal. The word animal is incredibly common. It's on millions and millions of web pages. Wikipedia, zoos, biology sites. Because it's everywhere, it has a very low IDF score. It's not a strong signal.
It's too generic.
Exactly. Like Jaguar, that's relatively rare. It appears in a much smaller slice of the web, so it gets a high IDF score.
So the algorithm is effectively saying, look, I don't care that much that you found the word animal. Everyone has that. I care a lot that you found jaguar.
Precisely. The perfect document is one where a rare word with a high IDF appears frequently with a high TF. That tells the system, this document is uniquely about this specific topic.
So now we have a score. We have a mathematical representation of my query, what I want, and one for the document, what exists. How do we actually compare them?
We go back to our geometry lesson. We have the query vector and the document vector. Both are basically arrows shooting out from the center of that 100,000 dimensional graph.
Okay, visualizing 2 arrows.
And to see they match, we measure the angle between them. This is called cosine similarity.
So if the arrows are pointing in the exact same direction,
The angle is 0. That's a perfect match.
and if one arrow is pointing at pizza and the other is pointing at shoes,
The angle is 90 degrees or wider. They're totally different. So the system just calculates this angle for every relevant document and ranks them. The smaller the angle, the higher the rank.
but there's a catch mentioned in the text, though, document length. If I write a 500-page dissertation, I'm probably going to mention almost every word at least once just by accident.
Yes, long documents have an unfair advantage just from sheer volume. So the text introduces something called pivoted normalization.
Which is a fancy way of saying, what, you handicap them?
Basically, it penalizes the score based on document length. So a short, punchy article that stays right on topic can beat a rambling 100-page PDF as long as the density of relevant information is better. It levels the playing field.
Okay, so up to this point, we've only looked at the content, the actual words on the page. But we all know the web isn't just text. It's a web. It's links.
And this was the big revolution. This is where we move from the bag of words to network analysis. Before Google came along with this idea, most search engines just looked at the text. But the web is a graph.
Enter PageRank.
The algorithm that changed everything.
Yeah.
PageRank treats a link from page A to page B as a vote. It says, if page A is linking to page B, it must think page B is valuable.
But not all votes are equal, are they? If I link to you from my personal blog that 3 people read, that shouldn't count as much as a link from, say, the New York Times.
Exactly. PageRank relies on prestige or centrality.
Right.
A vote from a high-prestige page counts for much more.
The text uses this random surfer analogy to explain how they calculate that prestige. I thought this was a great concept.
It's a brilliant thought experiment. Imagine a user who is just incredibly bored and has infinite time. They start on a random web page and they just click a link.
And then another.
And another. They never use the back button. They just keep surfing forward, drifting through the internet. If you simulate this random surfer taking 1 billion steps, where do they end up most often?
Well, logically, they're going to end up at the places that have the most roads leading to them. You know, Wikipedia, major news sites, the big hubs.
Right, because everyone links to them. So statistically, the surfer gets funneled there. Those pages have high page rank. And here's the key. If one of those big prestigious pages links to your tiny website, a chunk of their prestige flows right to you.
It's like a celebrity endorsement.
It is, but there's a nuance the text mentions, the dampening factor. Because real humans aren't robots. We don't just click links forever.
Right. Eventually I get bored, or I realize I'm in some weird part of the internet and I just type in a new URL.
The algorithm accounts for this. The dampening factor, which is usually set to about 0.85, it assumes there's an 85% chance you'll keep clicking links and a 15% chance you'll teleport, meaning you jump to a totally random new page.
And this stops the surfer from getting trapped in a loop, doesn't it? Like if page A links to page B and page B links right back to page A.
Exactly. Without the dampening factor, the surfer would just bounce back and forth forever, and those 2 pages would seem infinitely important. The teleportation breaks that loop.
Now here's what I found most fascinating about PageRank. The text calls it query independent.
That is a crucial distinction.
Yeah.
A page's PageRank score exists before you even type a search term. Wikipedia has a high PageRank right now, whether you're searching for it or not. It's a measure of global authority.
So when I actually search something, the engine is combining 2 different scores.
Yes, it looks at the relevance score. That's the TF, IDF stuff, the is this about Jaguars? And it combines it with the authority score, the PageRank, the is this a trustworthy site?
And you need both.
You absolutely need both. A page full of the word Jaguar with 0 links is probably spam. A page with 1 million links but no mention of Jaguar is irrelevant. You need that intersection.
So we've got the index, we've got the scores, the ranking, but what if the machine gets it wrong? I search Jaguar, I get the car, but I wanted the cat.
Then we enter the phase of refining. The system tries to learn from you. The text talks about relevance feedback and something called the Rokio algorithm.
The Rokio algorithm, is this where I have to manually click this was good, this was bad?
In the early academic models, yes. Explicit feedback. But nobody does that in real life. We're all too lazy. So modern systems use implicit feedback.
They watch what we click.
They watch everything. If you search Jaguar, you skip the first 3 links about cars, and then you click the 4th link about a zoo. The system takes a note.
It figures out, oh, he meant the animal.
And here is what the Rokio algorithm actually does conceptually. It goes back to that vector map. It takes your original query point, which was ambiguous, and it physically moves it.
It moves my query.
It shifts the coordinates. It moves your query vector closer to the zoo document you clicked on and further away from the car documents you skipped.
So it's effectively rewriting my search for me. I typed Jaguar, but the math in the background changes it to Jaguar plus zoo car.
In a sense, yes. And this has evolved into what the text calls learning to rank. Instead of engineers trying to manually tweak all the math formulas, they use machine learning. They just feed these massive logs of user clicks into an AI.
And the AI just figures out the patterns.
The AI learns when people type X and then they click Y, it means Z. We are effectively training the machine every single time we use it.
That brings us to the final piece of the puzzle then. How do the engineers know if their new algorithm is actually better? You can't just eyeball a billion results and say, yeah, that looks about right.
No, you can't build $1 trillion industry on vibes. You need a rigorous scientific standard. The text describes the Terra C conference, the text retrieval conference. It's like the Olympics for search algorithms.
They use human judges, right?
They do. They create a gold standard. They take a set of queries and a pool of documents, and a team of humans manually tags every single one. Relevant, not relevant, somewhat relevant.
So there's an answer key.
Yes. And once you have the answer key, you can run your algorithm and score it. But simple accuracy doesn't work.
Why not? I mean, if it finds the right document, isn't that accurate?
Well, imagine the right document is at position #50 on the list. Did the search engine find it? Technically, yes. But did it help you? No. You never scroll to page 5.
True. If it's not in the top 10, it might as well not exist.
Exactly. So they use a metric with a very intimidating name, NDCG.
Normalized discounted cumulative gain. It sounds like a tax code.
It does, but the concept is actually quite beautiful. It's a point system, but it's a decaying point system.
How does that work?
If your algorithm puts a relevant document at rank #1, you get full points. If you put it at rank #2, you get slightly fewer points. If you bury it at rank #10, you get very, very few points.
So the algorithm is heavily punished for burying the lead.
Exactly. The discounted part of the name means the value of a correct answer just drops off exponentially the further down the list it is. It forces the system to be confident and put the best stuff at the very top.
That makes total sense. It matches how we actually behave. We want the answer now.
We're impatient. And the metrics have to reflect that.
So looking at where this is all going, the text mentions a few future trends. One was task-oriented retrieval.
Right. We're moving away from just finding documents to getting things done. You don't just want to find a document about pizza. You want to order a pizza. The search engine is becoming an action engine.
And another one was social search.
Using community data. If your friends like this document or if people with your profile found this useful, then maybe you'll like it too. It's layering the social graph right on top of the web graph.
Which actually leads to this fascinating, almost philosophical point the text raises about personalization. We talked about how the vector moves based on my history.
The filter bubble.
Right. If the system is constantly using my history, my clicks, my location, my past queries to move the query vector closer to what I usually like,
Then you aren't searching the whole web anymore.
I'm searching a mirror.
That is the technical reality of it.
Yeah.
If you and I both search for a complex topic like climate change or economics, and the system knows our past preferences, it is going to serve us different documents.
And both lists are relevant mathematically. They both have high TF-IDF scores. They both have high PageRank.
But they present two different realities. Because the system is optimizing for your engagement, it wants to give you the result you are most likely to click on. And often, that means giving you back your own worldview.
So relevance isn't objective, it's subjective. And maximizing that relevance might actually kill discovery.
That is the trade-off. We want the convenience. We want the machine to know what we mean. But the price of that is that we might stop seeing the things we didn't even know we needed to see.
It's a lot to think about the next time you stare at that blinking cursor. It's not just a white box, it's a mirror, a map with 100,000 dimensions, and a massive popularity contest all rolling at once.
And it's getting smarter every single day.
Well, my brain is officially full. Thanks for taking the plunge with us on this deep dive into the mechanics of search.
Always a pleasure. See you next time.